Good day, everyone. Thank you for joining this webinar on Rohm Semiconductor's automotive PMIC products. My name is David Doan. I'm a Senior Product Marketing Manager and a member of the automotive marketing team with a focus on power management products. In this presentation, we'll give an overview of Rohm PMIC's lineup and roadmap, then touch on key features and performance of a few PMICs for ADAS applications. Data sheets and design-in collaterals are available on Rohm.com. For data sheets of parts that have not been released yet, you can request from the account manager, FAE, or myself. In this presentation, we'll focus on PMICs for ADAS applications. Rohm offers PMICs designed specifically for a particular type of sensing system, radar, camera, as well as PMICs for general computing systems such as domain controllers, ASICs, FPGAs. As listed here, we'll discuss 4 product families. First one is what we call scalable PMIC for compute engines, found in high-end clusters, domain controllers, machine vision systems. Second is PMICs for camera module powered by coax, so the input voltage could be up to 20 volts. Third is PMICs for radar subsystem, where output ripple and noise are important consideration. And lastly, PMICs for safety MCU. This grouping is meant to be only a broad guideline. For example, a radar PMIC can also be used as a power supply for an MCU or camera SoC. Similarly, we have a customer considering the safety of scalable PMIC to supply power to meet our high-end camera system. Scalable PMICs are intended to power a wide range of computing engines used in ADAS application, including very high-performance CPUs and FPGAs, which require hundreds of amps. This is for secondary side with input voltage from 2.7 to 5.5 volts. Outputs can be parallel and operate as multi-phase regulator. For example, 2 4 amps can be parallel to produce 8 amps, or they can be configured as controller to drive external power MOSFET or driver MOS, which can supply even higher current. For example, 20 amps parallel 2 of them can produce 40 amps. These are complex parts with many features because of the time limitation. In this presentation, we would like to cover the concept of scalability, outline some capabilities, and product differentiators. We'll skim through the next few slides with list main feature of individual ICs. As shown in picture, this family comprises 3 PMICs, 4 PMIC, sub-PMIC, and driver MOS. Depending on the number of power rails and output current required, customer can use 1, 2, or 3. Multiple instances of the same PMIC can also be used. For example, the picture in the lower right-hand corner shows 1 core PMIC, 2 sub-PMICs, and 2 driver MOS, all are designed to support SOD systems. When connected together via 2 wire integer bus, the IC acts as one synchronized unit, supplying 2 to 50 rails and up to 300 amps. Rails are power sequenced as if they all belong to one chip. The top 3 differentiators of this family are: 1 is scalability, modularity, and configurability. We mentioned mixing and matching the 3 ICs and using multiple instances of these to realize one big power unit, providing more power rails and more current. Configurability. Many configurations and operating parameters such as output voltage, power sequencing, OVP, UVP detection thresholds are set by OTP at a factory or E2-PROM, which could be programmed by customer. The E2-PROM setting can override OTP setting, and this allows fast prototyping. It also allows low volume production because customer wouldn't need to request a custom OTP mask from Rohm. The second differentiator is the good transient performance, which requires small output capacitance compared to competing parts. The last differentiator is ASIL-B support. There are extensive monitoring and protection circuits inside a chip, including built-in cell test, redundant voltage reference voltage, parity protected I2C, ECC protected E2-PROM. This slide shows example of various combinations of PMICs in this family to build power supplies for a range of power level, from 5 rails, 15 amps with one IC, to 40, 50 rails, and hundreds of amps with multiple ICs. One main PMIC can supply 5 rails, 40 CDC, 3 LDOs, and a total of 15 amps. Example 1 here shows one main PMIC with two 10 amp driver MOS to supply a total of 28 amps. Example 3 shows swapping out 10 amp driver MOS for 20 amp version. We'll bump that up to 58 amps. Box 4 and 3 are configured for two-phase operation to supply 8 amps. This configuration would be good for an SoC or FPGA, which may require only 2 or 3 high current rails for the digital core, AI engine, and high-speed serial I/O, and the rest of the rails are a few amps at most. Example 5 on the right side here shows 6 PMICs connected to the primary PMICs to vastly expand the number of rails and power capability. Thanks to the interchip link, they can be power sequenced as one unit. And similarly, the faults detected in one IC and one of the secondary IC will be reported to a primary IC, which interfaces to the whole CPU. The main PMIC, BD96A01, has 4 bucks, 3 LDOs. The bucks can operate at 2.25 or 4 MHz, allowing trade-off between efficiency, size, and output ripple. They can be synchronized to an external clock. Spread clocking is also an option. Output accuracy plus minus 1.2%. They all support DVFS. The output step size of 5 mV. Box 1 and 2 can each supply 2 amps and can be tied together to support 4 amps, each of which can also be configured as controller for a driver MOS outside. The LDOs are 300 mA each, and they can be configured as low switches or as LPDDR5 termination. The functional safety includes, and this is not an exhaustive list, OVP, UVP, OCP with auto threshold configurables, the watchdog with Q&A, built-in cell test, mutual monitoring of resonant voltage and oscillator. The I2C transaction are CRC protected, while E2 prom is ECC protected. It is designed to operate from -40 to 125 C ambient temperature. The maximum junction temperature 150 C. It comes in 6x6 48 pin QFN. PMIC BD96A02 has only 2 bucks, which can provide 5 amp each or 10 amp together when configured for multi-phase. The electrical specs and functional safety features are the same as those in the main PMICs we just covered. Think of this PMIC as an easy way to add additional high current rails to the system as needed: 5 amps, 10 amps, 20 amps, or 40 amps. The drive MOS BD96340 is for when you need more than 10 amp per rail. The PMIC box then works as PWM controller for the external drive MOS power stage. This partition is done for both scalability and thermal reasons. You can swap out for a different drive MOS when you need more or less current. BD96340 can supply 20 amps continuously and 30 amp peak. There will be a 10 amp version shortly. Then we will introduce other variation depending on market demand. The driver MOS has iSense output for the controller to monitor its output current and eye temperature. It also has on-chip protection such as UVLO, output voltage, OCP. We now turn to PMICs used for sensing system. This slide shows PMICs for cameras, and our focus today is on the BD968A and B series in the middle and marked with green dots. The previous generation, BD86852, is large and lacks functional safety. Future devices on the roadmap, marked yellow here, will either incorporate more power rails or comes in smaller package. BD868A0 is an ASIL-B compliant PMIC for camera systems powered by coaxial cable. Input voltage range is 4 volt to 20 volt. It provides 4 power rails, 3 DC-DC, 1 LDO. To supply the ISP imagers and serializer, switching frequencies to 0.25 MHz with a spread spectrum option. One primary DC-DC down converted coax power to lower secondary voltage, from which the two buck regulators and LDO will generate a low voltage for the load. The LDO can be used to power the CMOS imager or serializer. All output voltage are OTP configurable. The default values are shown here along with the range. Power sequencing is also OTP configurable, so this PMIC can be used with different ISPs and imagers. Functional safety support includes the build self-test for analog and digital circuitry, CRC protected I2C, UVP, OVP monitoring of power rails. To support different system design, many parameters are OTP and or I2C programmable, including UVLO threshold, UVP, OVP threshold, masking time, power on delays, discharge resistance, error handling. The PMIC is intended to go into small camera module, which could be mounted on a windshield and exposed to sunlight. Therefore, it's designed to operate in ambient temperature at up to 125 C. Camera module tends to be space constrained. This slide shows board layout and board list. The IC is in 3.5 by 3.5 mm, 20-pin QFN package. There are only 15 components on the board list, and the solution footprint is only 10 by 10 mm. The last part of this presentation is on PMICs for radar modules. As can be seen on this slide, the previous generation has a primary DC-DC controller, which allows PMIC to work directly off the battery. The current generation, BD391XX and its follow-on 392XX, works with input voltage of 5 V or lower. This is in keeping with the power architecture of lead customers. The focus of current gen is on small size and ASIL-B support, so the primary controller becomes a secondary buck and integrated power FET in this generation. BD391XX has 3 bucks and 1 boost, 5 V intended for the CAN interface. Switching frequency can be 2.25 or 4 MHz to allow trading efficiency for small output ripple. Spread spectrum is an option to minimize the interference to the radar MIMIC. The center spread 2 to 4% and the modulated frequency is also selectable between 4 and 8 kHz. The output voltage, the power on sequencing, and many other parameters are also OTP configurable. Please note that the input voltage range is 2.5 to 4.5 and not 5 V. The buck regulators in this PMIC incorporate low noise switching technology that allows them to power sensor directly with external LC filter rather than LDO, saving cost and power. We'll talk more about this in the later slide. Support for functional safety includes base beam self-test, window type watchdog timer, OVP, UVP power rail monitoring. The output accuracy plus minus 2%, while the monitoring accuracy is plus minus 1.5%. It is designed to operate in ambient temperature of minus 40 to 125 C. Package is 4x4 flip chip QFN to minimize package parasitic inductance and resistance. BD392XX is a variant of 391 with some improvement. It uses the same IPs and has more or less the same electrical characteristic except for the following differences. It has one less DC-DC, so only 2 bucks and 1 boost. In return, it can monitor 2 external rails. One example use case is when a MIMIC needs a higher current than can be provided by 391 DC-DC. In that case, the higher current discrete can be used, and it will be monitored by the 392. 392 will also have ASIL-C support. The output voltage accuracy is improved from 2% to 1%, and the monitoring accuracy will be better as well, plus minus 1%. But it will have a narrow voltage range, 3 to 4.5 volts. It will also come in smaller package, 3.5 by 3.5 mm. These graphs shows efficiencies that alter box at different frequencies and temperatures. Efficiency stays between mid-80s and 90%. Please note that the high temperature here is 140 C or 125 C. DJ max is 150 C. Perhaps you can inspect the data later. We will now touch on the low noise switching DC-DC mentioned earlier. Radar PMICs require low noise power supplies. One can save cost and power if there's no need to use LDO to reduce noise from a switching regulator. The 3 boxes inside radar PMICs are designed for low noise, such that an external LC filter will be enough to reduce the noise to acceptable level for most applications. Referring to the graph on the right, the faint blue curve is a noise spectral density in nanovolts square root of a normal buck converter. The yellow curve is noise of the low noise buck in this PMIC. You can see that this output still contains high frequency noise around 1 MHz, and the spike close to 10 MHz. The red curve shows this noise is suppressed to a very low 10 nanovolts square root of an LC filter. Using 1 volt 2 amp rail as an example, using LC filter instead of an LDO, you an area saving of 34%, a dramatic reduction in power from 0.6 to 0.04 watt. Is due to a high current used in this example, but even if you are using only a few hundred milliamps, the power saving is still significant. That's all we have for today. We hope you find this overview helpful and hope one of these will be suitable for your next design. Please don't hesitate to let us know should you have questions. Thank you again for your time today.